Hello, welcome to this talk on Bespoke Cache Enclaves, a fine-grained and scalable partitioning-based defense against cache side channels. My name is Gururaj Saileshwar, and this is work done in collaboration with Sanjay Kariyappa and my advisor Qureshi from Georgia Tech. In this talk, I'll tell you three things. What are cache side channel attacks and why are they such a big problem? Why existing cache partitioning-based defenses have practical challenges? And how we enable a scalable and flexible cache partitioning-based defense using Bespoke Cache Enclaves. Processor caches improve performance by providing fast access to cache data and avoiding slow DRAM access. However, the timing difference between a cache hit and a cache miss results in timing side channels, a security problem. Our focus is on the shared last-level caches, as they're typically shared between multiple processor cores in security domains in cloud computing systems and are particularly vulnerable to cross-domain side channel attacks. There are three main classes of cache side channels. First and most potent class of side channels is conflict-based attacks, like prime and probe, which exploit sharing of cache sets between the victim and the spy. In these attacks, the spy observes victim data accesses based on which of its lines gets a conflict on a shared set with the victim and gets evicted from the cache when the victim line is installed. The second class of cache side channel attacks are shared memory attacks like flush reload or flush flush, which are the most accurate attacks. These exploit sharing of cache lines for shared memory between the victim and the spy. In these attacks, the spy is able to learn a victim's data accesses by directly observing hits on cache lines installed by the victim. Lastly, the recently discovered cache occupancy-based attacks are the third and the most generic attacks, where the spy simply exploits sharing of the limited cache space with the victim. Here, the spy is able to fingerprint victim's execution by simply observing how much of its working set gets evicted when the victim program executes. In general, using cache side channel attacks, a spy can leak victim secrets like AES or RSA keys, user keystrokes, confidential IP, etc., and also cause privacy breaches like fingerprinting a victim activity. So they are a serious security problem. In recent years, several secure cache defenses have emerged to mitigate cache side channels, and they broadly fall under two categories: randomization-based and partitioning-based. Randomization-based defenses obfuscate the mapping of addresses to sets to defeat conflict-based attacks, and also use duplication of shared lines across domains to eliminate shared memory-based attacks. But they still allow sharing of the limited cache space between different domains, so they continue to be vulnerable to cache occupancy-based attacks. In comparison, partitioning-based defenses offer much more principled defense against all cache side channels, as they completely insulate the cache state of different domains and prevent any cross-domain hits, evictions, or even replacement state updates across domains, thus preventing any information leakage. Hence, this is the focus of our work. However, existing partitioning-based defenses face severe practicality challenges and hence have had limited adoption in real-world software. Let's see why. A cache is a two-dimensional structure, so it can be split along ways or sets. Way partitioning-based solutions, like Catalyst or Dog, divide the cache along ways and allocate one or more ways to each individual security domain. However, such solutions are limited in terms of scalability, as the number of domains that they can support are limited by the LLC associativity. For instance, a 16-way LLC can only support 16 domains at a time. And this is insufficient because an LLC itself might be shared by 32 to 64 cores simultaneously. Page coloring, on the other hand, partitions the caches along sets. By associating colors for DRAM pages mapping to disjoint sets and allotting pages of different colors to different security domains, it ensures that domains use non-overlapping cache sets. But this design suffers from limited flexibility. It requires the DRAM and cache allocations to be in the same ratio. For instance, for a program to occupy half of the LLC sets, it would be allocated half of the DRAM. but an application's footprint and a data locality might be totally uncorrelated. These flexibility and scalability limitations have limited the adoption of cache partitioning as a defense in real-world software like web browsers. So our goal is to enable a practical cache partitioning defense that can scale to hundreds of simultaneous security domains where cache allocations can be flexibly managed independent of DRAM allocations. And finally, it should also allow fine granularity cache allocation sizes, given that sensitive programs often have footprints of few kilobytes. Let's see how we enable this. Our solution enables Bespoke Cache Enclaves. We define cache enclaves as isolated set partitions of arbitrary size which are non-overlapping in the cache. So each security domain can be allocated a cache enclave. These enclaves are allocated at the granularity of a cluster or a group of 64 sets. So they are much finer granularity allocations than, say, wave partitioning. The cache enclaves allocated to a domain can also be sized independent of the DRAM allocations. So they are flexible, unlike page coloring. Lastly, our framework supports up to 512 bespoke cache enclaves in the cache simultaneously, which is much larger than the 16 to 32 domains supported by wave partition. So our solution supports all our goals for cache partitioning. However, there are two key challenges to enable this solution: security and performance. For security, how do we ensure that only the lines of a domain map to its own cache enclave? And for performance, how do we uniformly map the lines within an arbitrary sized enclave? The key insight to both of these challenges, to solving both of these challenges, is flexible dynamic indexing. Let's see how this works. The division of responsibilities in BCE are as follows. The OS is responsible for deciding how large a cache enclave for a domain is going to be, and the hardware is responsible for allocating the clusters for each enclave in the appropriate physical locations in the LLC. The interface between the OS and hardware is via new privilege instructions for allocation and deallocation of a cache enclave. So the hardware is responsible for mapping line addresses to the physical location of the clusters in the LLC. This task is performed by virtualizing the mapping of clusters. First, we have a load balancing hash, or LBH, that maps line addresses to the clusters of a domain. We call these logical clusters. And then we have a cluster indirection module, or SIM, that maps logical clusters of a domain to the physical clusters in the LLC. In other words, it maps LCIDs to PCIDs. The load balancing hash is constructed using multiple randomizing hashes that uniformly map lines to clusters of a domain even when the number of clusters is a non-power of 2. This is important for minimizing set conflicts and boosting performance. The SIM's indirection from logical clusters to physical clusters in the LLC is performed with the help of lookup tables, which store one-to-one bijective mappings. This ensures that there is no overlap between the clusters allocated to different domains and provides strict isolation guarantees between domains where the state updates of one domain, like hits, misses, or replacement state updates, have no effect on the cache state of other domains. We provide several additional details about the construction of the load balancing hash and cluster indirection module in the paper, but I would like to highlight two important details. First, our hardware is carefully designed for security. For instance, even the cluster indirection module, which is shared across multiple domains, is designed to be constant time lookup to prevent any new side channels, unlike prior works. And there is no reliance on the OS for the security. It is completely enforced by hardware. Second, the storage overheads of our solution are minimal, less than 2% of the SRAM area. So combined with the scalability and flexibility benefits, our primitives are quite practical for adoption by real-world software. Next, we look at results. To evaluate the benefits of fine-grained cache allocations, we performed a case study using a mix of cache-friendly and insensitive workloads. With a trace-based simulation of 16-core 32 MB LLC, we ran 15 copies of cache-insensitive PageRank and 1 copy of cache-friendly ROMs, and compared the relative performance of BCE with DOM. Dog can only allocate equal sized 2 MB partitions which are direct map for all the domains. In comparison, BCE can also do such equipartitioning but provide 16-way partitions which result in 5% higher IPC for the cache-friendly ROMs workload. But BCE can also customize the partition sizes as per the workload requirement. For instance, BCE can have several configurations where the PageRank LLC allocation is squeezed and the ROM's LLC allocation is increased, and this can boost ROM's performance by up to 40% compared to DOG, while keeping the impact on the IPC of PageRank negligible. Thus, the fine-grained cache allocations that are customizable for BCE are extremely beneficial for performance. For overall performance, we consider 3 configurations: DOG, page coloring, and BCE with equal partitioning, and compare the slowdowns versus a non-secure baseline with an unpartitioned LLC. Overall, BCE has a comparable slowdown as page coloring, while allowing LLC allocations to be managed independent of DRAM allocations. In comparison, DOG has a higher average slowdown and a much higher worst case slowdown compared to BCE, as it is forced to provide direct map partitions when the number of ways equals the number of domains, unlike BCE. Additional evaluations covering the LLC misses, LLC lookup latency, and storage overhead breakdown are provided in the paper. Please check it out. In summary, we discussed how cache partitioning is a principal defense against all types of cache side channels. But prior cache partitioning based defenses are impractical either due to limited scalability or limited flexibility. We proposed Bespoke Cache Enclaves, a flexible set partitioning based defense via dynamic indexing. It is highly practical because of its scalability, fine-grained allocation capability, and the ability to be managed independent of DRAM allocations. Its fine-grained allocations are highly beneficial for performance, and it comes with negligible costs. So we believe that Bespoke Cache Enclave primitives are highly suited for practical adoption by real-world software and hardware. Thank you for your time, and I'm happy to take questions.